So today we have Zach Taylor, who is a structural engineer at Kimley-Horn. For those of you who don't know Zach, he is a performance-driven structural engineer with years of professional experience. He has worked for Michael Baker International, JUB Engineers, and is currently working at Kimley-Horn. He is skilled in structural engineering and has worked on many projects to manage concept, layout, design, detailing specifications, and construction documents for many structural and roadway projects. So Zach, I'm going to go ahead and give you the presentation mode and we can get started.
Awesome, thanks Lucy. Let me make sure I'm showing the right monitor here. Okay, I think we got it.
Yep, I see your screen.
Awesome. All right, well, thank you for that introduction, Lucy, and thanks for everybody who's made it out today for the session. Excited for the opportunity to share a few things that I've learned about boundary conditions over the years, and hope that there'll be some opportunity at the end for some good interaction, some questions, things like that. I'm very much somebody who would prefer to do these live, but just due to the number of attendees, I know that's tough because just to have that back and forth constantly going on. So I'll try to keep this first part short and then get into some questions and discussion towards the second half. So today we're going to talk about just some general application of boundary conditions. And as Lucy mentioned, so my background's in bridge, and I assume that's the same for the majority of y'all. But the examples I share are going to be more related to that, but at the same time, these principles apply more broadly for pretty much any structure you plan to model. So, all right, so today I'm going to just give you a quick overview of what I plan to cover, and then before we get into the question and answer portion. So first off, I want to cover a little bit about why boundary conditions are so important, and then talk about some general boundary condition background and the tools available in MIDAS to accomplish establishing boundary conditions. We'll cover some typical real-world applications of boundary conditions for bridges, and then talk a little bit about how to determine some tips and tricks, I guess, for determining boundary conditions, and then spend a little bit of time talking about what happens when we get it wrong, or more accurately, common pitfalls, or how do we often get it wrong when we're establishing boundary conditions. And then we'll cover a few examples of some interesting applications that I've seen throughout my career. And then after we go through that, I plan to leave a good amount of time for questions and comments. So first off, getting into why boundary conditions are important. So as most of you probably are aware, boundary conditions are fundamental to FEA modeling. And I'm sure that you've all experienced it at one time or another where if you don't have a boundary condition in the right place, your model essentially won't work. You have to have boundary conditions in order to model. And so they really do exactly what their name implies. They establish the boundaries for how the behavior of your model. So FEA is at its core a stiffness problem in the end, and without boundary conditions, you can't solve a stiffness problem. Your boundary conditions directly introduce or remove stiffness from your system, and oftentimes this can have drastic effects and impacts on how your model behaves. So it's critical that you establish the correct stiffnesses so that your loads will go where you expect them to go within your structure, and this will ultimately inform design decisions, because you're going to size members and establish design parameters, criteria off of how that load moves through your structure. So it's extremely important that we get it right. A good model approximates the physical behavior of a real world structure. And I think the key word here is that it approximates it. It's important to note that your model is never going to be perfect. But unless it's a super basic model, in which case you might ask yourself if you even need a model at all. But most of us are using FEA because the behavior of our structure is going to be hard to predict using a traditional analysis method. But in the end, it's important to realize that your model doesn't have to be perfect. It really just needs to be good enough to get you a reasonable solution within a reasonable margin of accuracy. And I know that's a nice, real solid, precise answer. And as engineers, we love that fluffy gray area. But the truth is that with FEA, you're often operating in that gray area to some degree. And to use everyone's favorite phrase, there's a lot of engineering judgment that goes on when you're making decisions about how to establish boundary conditions. So to get the right answer, we need to be thinking beyond overly simplified, idealized theoretical models. Now, that's not to say they're not useful and not helpful or informative to use those as a reference, but once again, you're probably working with something that's got complex geometry or something that's out of the norm. So you need to have a good understanding of what your real world structure behavior generally should look like. So you can ask yourself, what's real? What can I expect to see at the end? You kind of need to have a general idea of what the answer should look like, and then the model can give you all the specifics, the numbers, everything behind it that you need to do your actual design. In the end, a solid understanding of boundary conditions is so important because it is one of the most common places that I see people get it wrong is establishing boundary conditions. So I want to keep this part a little short because I'm sure y'all are very familiar with most of these, but I think it's worth going through them and kind of showing where they are within MIDAS. But I would think of these boundary conditions.
Sorry, are you presenting on a presentation slide right now?
Can you not see my screen?
No, I see I thought you were showing I see the Midas one.
Oh, you see the MIDAS screen with the
With the yeah, with the
bridge? Oh god, so you guys haven't seen any of the other slides.
No,
I
sorry.
got the wrong screen showing here. Here, what if I
If you go to sharing, you should be able to change your screen if you're using multiple screens. If not, just pull over the PPT to wherever you have the Midas software up.
okay, here we go. Is
There you
that
go.
better?
Yep, now I see it.
Well,
Thanks.
you didn't miss anything. I'll tell you, those slides weren't pretty. It's just words. So, but apologies for the just having to listen to my voice and look at a bridge model the whole time. Anyway, so I guess we're talking about boundary conditions as a general rule. So the basics are fixed, pin, roller free. I mean, these types of basic boundary conditions, which everyone's very familiar with. Now, you could really boil everything down to their most basic state for boundary conditions as fixed or free, or some combination of that, which is where pin and roller comes from. But everything else with regard to boundary conditions kind of lands somewhere in the gray area between these basics. Some variations on the basics would be like a spring. A spring fills in the gaps between the basic boundary conditions. Some variations of springs. You've got linear springs, which are the same stiffness generally in both directions for translation or rotation. This is what most people commonly think of when they think of a spring. There's also, within MIDAS, you have tension or compression springs, which are similar to a linear spring, but they only activate in one direction and provide no support in the other directions. Non-linear spring is one that varies, the stiffness varies with how much it moves. So as you stretch the spring, it either gets stiffer or softer. And then you can even apply damping to springs just to add another layer of complexity there. And then you have your links, and what makes the links different than a support condition like a spring, a fixed or pin or a spring that's attached to a node, that's a support condition. You have links which connect two nodes. So a rigid link would connect two nodes rigidly, and an elastic link is like a spring version. So you have links and supports. And then you also have end releases. So the default for anytime you're modeling in MIDAS is when you connect two beam elements together, it connects them rigidly with the properties of the stiffness properties of the elements that are being connected together. So if you want to, for some reason, you want to provide a different condition there, like a hinge or something where the behavior isn't like a fixed connection, you have to assign a beam end release to that, and that can allow different types of behavior at locations where beam elements come together or plate elements. And then a couple other things I wanted to highlight were beam offsets and local axes, because I feel like those are important in establishing boundary conditions. Beam offsets, yeah, I've used these a couple times, but they're not super common, I would say. But a beam offset can be useful in the sense that when you're modeling, we're using beam elements that don't have necessarily a dimensional aspect to them. I mean, they do along the length of the beam, but the beam dimensions itself aren't necessarily accounted for. And there are times where those offsets between, or those dimensions, are important to the stiffness of the system. And so you have an option to establish beam offsets using that tool. And then local axes is a nice tool that can help simplify the way you assign your boundary conditions, because there are times where you may want to apply boundary conditions along a different axis than or coordinate system than what the global coordinate system is. If you have like a skew or something like that, local axes can help simplify the way you apply your boundary conditions. So really quickly, I'll bring this screen back that y'all are sick of seeing already, and just kind of show you where those conditions exist. So your supports are here. Very simple way to apply your basic support that we talked about. Then you have your springs where you can assign different spring stiffnesses. It's very similar, but a little bit more robust than your basic support conditions. And then you have one that establishes it for your plates if you're using plates. And then just a couple other options here. This integral bridge is kind of nice if you're doing integral bridge modeling. I don't typically model integral bridges in MIDAS, but if you, for some reason, you want to model them in, it can give you your soil springs along the back edges and then rotational springs at the piles. And it's a really nice tool to help you model that quickly and efficiently. Then you have your links section, which you basically treat it very similar to how you would establish a point spring or a support. So that's for elastic links, rigid links, and then there's some general, this general links tool you can use to be a little bit more generic if you want to. Beam end releases, it's all the same. You just apply your either fixity by checking the boxes, or you can assign a value for that stiffness that you want to apply to that beam end release. So speaking of boundary conditions, let's see. I think that covers what I wanted to get through. But when we're talking about bridge boundary conditions, here are some real world applications for how you can establish those. The first in the top left, I'm not going to go through all these necessarily, but this is an elastomeric bearing. And what's interesting is that you can apply boundary conditions in different ways that allow you can apply, for example, on an elastomeric bearing, a stiffness to that, or you can treat it as a free to translate, or you can apply a rotational spring to it. There's a lot of different things you can do with an elastomeric bearing, and it really just depends on the results you're trying to get. what you would want to apply in your model. And then a couple other examples: a rocker bearing here, which doesn't have as much flexibility in how you can treat the boundary conditions. Sliding bearing, which is an interesting one, because up to the point where you have a friction release, you could model this as a spring if you wanted to, because it provides resistance up to a certain point. Again, depends on what you're trying to accomplish with your model. A typical, well, I wouldn't say typical, but a roller bearing for a large bridge there. And then you have a sliding plate bearing here on the left. And then these three on the bottom right are examples of an end condition for a beam. So there's the pin and hanger that is a way to release moment within the beam. And then you have a typical pinned connection between a framed in element that you would treat also as a beam end release in a model. And then you have your splice, which is of course a fixed type connection. So just some examples of application. So how do we determine boundary conditions? Here I've listed just a few of the tips that I use when helping to help me set my boundary conditions. So the first thing I do with every model is I always think through each boundary condition individually. That's not to say that you can't apply them, in mass in your program, and we don't have to apply them one by one, but it is good to kind of map it out on paper and figure out, look at each one individually and figure out what's really happening at that location. It can be really easy to make a blanket assumption. Like, for instance, if you were doing an integral bridge, which oftentimes if you're designing an integral bridge, you're not necessarily modeling it, but you might assume that you should go with a pin and a roller because that's how you would typically design the girders for an integral bridge. However, what if you're modeling it for the intent to have a deck pour sequence that may fix one of the ends before you get to the final loading condition? And I'm just throwing out hypotheticals here, but if you were to model that with a pin and a roller, you may not capture all the conditions or all of the behavior that you're specifically trying to capture. So if you don't carefully consider what's going on with your specific instance, it's really easy to overlook or forget about something that you need to account for in your boundary conditions. So think about how the structure would behave in the real world. Ask yourself questions like, if I push on this, will it move? Is it gonna push back? How much will it push back? Is it significant enough that I need to capture that? Does this part of my structure, when it moves, drag another piece along with it? Maybe I need to link those two together, or and which one of those elements controls the movement? Is one of them going to have more influence over the other? These are the types of questions that'll help you get your boundary conditions right. Think about what information you want out of your model and how the boundary conditions might affect that information. Are you just looking for deflections, for example, or are you looking for member force demands so that you can design that member? So a good example of this would be, again, going with a simple beam example. If you have vertical supports for your simple beam and you're trying to decide if that support should be a vertically rigid or if you should model it as a vertical spring. Well, if you're just looking for bending moment and shear in the beam, does it matter if it's fixed or a spring? Is that even going to impact the bending moment and shear demands? Not really. But if I want to understand the total displacement of the system, particularly at the supports, are you going to get accurate results if you model them as rigid? Definitely not. So you just need to take it as far as necessary in order to get accurate results for the things you actually care about. And so that's an important piece. And then probably for me, probably the most important thing in determining boundary conditions is just testing things as I go. See if the structure behaves like you expect it to when you load it. This requires some understanding of load path and and definitely structure behavior. So it's good to make sure you have some idea before you go in of what you expect to see when you get to the end. And to be fair, when you're using FEA, a lot of times you may not know the end answer, but you also do have fundamental knowledge of structural behavior that you can use to use some deductive reasoning and determine maybe what it shouldn't look like. Definitely had situations where I don't necessarily know what I'm looking for, but I know for sure that the structure shouldn't be behaving in a certain way, and that I've got a boundary condition issue. So breaking things down piece by piece and testing them, testing the movement of the structure is a really good way to figure out if you've done it right. So what happens if we get it wrong, or what are some typical ways that we do get it wrong, and pitfalls to watch out for? I'd say watch your tendency to assign boundary conditions because something's typically done a certain way. Once again, kind of rehashing this, but we've established that we're probably doing something outside the norm, so maybe your boundary conditions aren't going to be so typical. So just keep that in mind. Most of the time, I would say beware of the worst case. A lot of times when we're engineering things, we look at things and say, oh, well, it's worst case scenario, so we should be covered. But if you're dealing with boundary conditions, there's no such thing as a worst case scenario. There's always, I mean, there may be a worst case scenario for a very specific application, but there's always a trade-off one way or the other. For example, going back to the simple beam, a beam with pinned ends might create a worst case scenario for the moment demand, but then what about your connections, right? If your connections are collecting load, you may be underestimating what's happening at the connections. So you have to make sure that what you're modeling jives with your design methodology as well. Because if you decide to fix those ends, now your moment goes down in your beam, but your connections are getting hammered. So it really just, again, once again, depends on what you're looking to get out of your model and being aware of what those trade-offs are before you decide what is your worst case. Another common pitfall is what I like to call the Princess Bride syndrome, otherwise known as I do not think it means what you think it means. So I apologize for those who don't know that reference, but it's from one of my favorite movies. Highly recommend it if you get a chance. Princess Bride. Anyway, I digress a bit, but essentially this pitfall is where you can actually be applying a boundary condition that you think is going to behave a certain way just because of what it's called. You know, you might be assigning something to be pinned, but because of the way you apply boundary conditions elsewhere in your model, you may actually be creating a condition that behaves more like it's fixed. So you have to be aware of how other boundary conditions are influencing the one that you're assigning. And so you may not, just because the program says it's a pin doesn't mean it's going to act like a pin, right? So be aware of the big picture and how it's behaving, and once again, test it. Make sure it's behaving the way you think. Relative stiffness is another place where we can get tripped up. When something's modeled as fixed, the program's going to treat it as essentially infinitely stiff, as much as it can. And so if you end up with a boundary condition that includes a lot of infinitely stiff supports very close to another, or infinitely stiff supports very close to one another, and then you have another nearby stiffness that it's relevant, but because you've got all these infinitely stiff boundary conditions right close to it, the stiffness, the softer stiffness, feels very soft in comparison. And so you could end up with results that don't really reflect reality, because nothing that we deal with in real life is infinitely stiff, right? There's always some sort of stiffness. And so that relative stiffness can cause issues. This is one of the reasons you'll hear people talk about making sure your mesh is relatively consistent. I've seen examples of problems where you have two beam elements, a long one right next to a super short one, maybe imperceptibly short, and then you get a load spike in that location just because there's a relative stiffness issue between those two pieces. So definitely be aware of that as you're establishing your boundary conditions. So this is kind of a random example I pulled. I was kind of doing a little bit of research on this, and I liked this example because it illustrates a red flag, I would say, that it can often help you get to the right answer. So this is an example of a model that's the exact same model, but has different boundary conditions. And the loads on the left-hand side are very concentrated in comparison with the loads on the right. And it's all due to the way the boundary conditions were established. This example had up to 1,500% difference between the results using the same model. So a red flag, I would say, anytime you see massive force concentrations, definitely something to look at. Is that actually real? Because again, the relative stiffness issue comes into play. So this is an example of a project that we're working on out of our Arizona office, where we have some girders framing into an exterior girder. And as I discussed earlier, the default condition for connecting beam elements together is that it treats them as fixed, internally fixed. And so when you model something like this, if you want it to behave that way, that's great. But then you have to be aware of what that's doing to your beam, like what types of loads that's introducing. Or do you need to establish a boundary condition that treats this more like a pin rather than a fixed connection? So things to consider when you're modeling. Not going to go about trying to determine what the right answer is on a lot of these. Just want to use them as an illustrative example. So another project I was doing where we had a seismic analysis on a curved steel bridge, and I got some really strange reactions at the abutments. And I wish I had saved a screenshot of this, but I kid you not, the pile reactions looked like kind of like this. It was all over the place. This is just a made up sketch, but I could tell right away just by looking at it something was off. But I wasn't sure what was causing the problem. I remember running through a bunch of different things to try and resolve it, and I don't even remember exactly what it was that caused the issue, but I do remember that all I had ended up having to do to fix it was a simple boundary condition change. I have modeled the piles as if they were fixed vertically, and just changing that one degree of freedom to be a vertical spring, which I assumed still as very, very stiff, by the way. It was essentially behaving as if it was fixed. I think the displacements were negligible, but because I made it not infinitely stiff, it allowed the structure to move just enough to redistribute the loads and ended up giving me a result that evened out. And so this is a good example of how relative stiffness can kind of create an unexpected result at times. So another example, and I have to give credit to Daniel Baxter and Shayla Olson with Michael Baker International for this one. They did a webinar recently that covered strut and tie modeling, and I thought this was a great example of a unique way to apply boundary conditions to get more accurate results out of your model. So this example is a strut and tie model of a pier cap. Oftentimes engineers will just take this and say, okay, I'm going to put a pin at one end and then rollers at each of the column supports. But in this case, there's moments at the tops of the columns that are going to transfer into the pier cap. And if you model them as rollers, then you're not capturing that effect. And so in this case, the engineer determined that vertical reactions. So they established a pin and a roller at one pin, one roller at each of the ends, because as we know, you have to have boundary conditions to have a model that works. But they calculated the reactions that would be at those columns, and then they were able to modify those reactions in a way to introduce the force couple and make sure that those moments were transferred to the pier cap appropriately and get them more accurate results. And then this is a really basic example that shows how boundary conditions can create force concentrations. The bottom corner of this example is extremely stiff because you're fully fixed along two edges. And so when the top corner of the plate is displaced, the bending moment concentrates near the top left and the bottom right corners. And this behavior is real in an idealized world, but the actual behavior of a structure can definitely vary. So for example, if this structure was made out of concrete and you developed a large force concentration near the top left corner or the bottom right corner, which is also extremely common in problems where you have openings with sharp corners, the force will concentrate. And will it actually concentrate like this in the real world? Likely no, because the concrete, if it concentrates that high in those areas, will start to crack. And when that happens, the boundary conditions change in real time and the forces redistribute. So if the structure's steel, it's not as susceptible to the same type of cracking that concrete is, but its properties are such that if it does crack, it's a much bigger issue than if concrete cracks. If concrete cracks, the steel can just carry the load, help redistribute the load to other areas, and you haven't necessarily compromised your structure in any kind of way. But steel is a whole different animal if you develop cracks, which is why you see in steel avoiding high stress concentrations is extremely important. Granted, we want to do that always, but it's not the same issue, you know, depending on the scenario. So it's good to just have an understanding of how boundary conditions can affect these things and how they change in real time with respect to real world application. So I think that pretty much covers what I wanted to get through. So at this point, I think let's just open it up to any questions people have or comments or anything anybody wants to add to this. Love to hear your feedback.
Okay, I think people are still typing. Give it 1 second. A lot of people had questions about your slides.
You want me to go back? I can go back.
If you want, it's just I think most of them. Oh, okay, they're starting to come in. Most of them were just kind of confused but weren't sure. But yeah, we have our first question. It's actually a two-parter. Let me just pull it up. Okay. Sorry, give me 1 second. We're getting a lot of questions now. Okay, so we'll start with these. I'm going to update this in a second, but the first question we got was, what boundary conditions would you use to model floating elastometric bearings when performing a seismic dynamic analysis?
Oh, good question. I think the answer for me is it really depends. Again, I hate to use that cop-out answer, but it depends. So if you're using an elastomeric pad, it depends on what you want that elastomeric bearing to do in a seismic application. Because I've used seismic or elastomeric pads where I've also designed them to be fixed in an earthquake, but I want the elastomeric pad there for the vertical bearing. Or sometimes you use them to, I've used sliding bearings with elastomeric pads where, you know, under normal strength conditions, you may be loading something up and you don't expect that your sliding bearing is going to slip under normal loading conditions, but it may still have some stiffness. So in that scenario, I may want to model it as a spring. But under a seismic analysis, I'm expecting that it's going to slip, and so I'm going to model it as free to translate. So you can also have, you know, elastomeric bearings they take a lot of forms. I mean, even a seismic isolation bearing uses elastomeric material. So, you know, in that scenario, likely you're going to model it as a spring. You're going to have properties that you want to assign to it based on what you get from the fabricators who are making that pad, and you want to assign those stiffness parameters. So I know that's kind of a roundabout answer, but it really can vary greatly if you're doing a seismic analysis, how you want to model that. So I hope that answers the question. If you have a follow-up, let me know.
Okay. I'm Zach, sorry. I'm gonna we're still adding the questions to the PPT so I can share my screen. So give us like a minute. In the meantime though, for our attendees, if you guys can just um fill out this really quick questionnaire. It's just one question. I'll give you guys like a minute while we set up all these questions, and then we will go back to the questions momentarily. Okay, just 5 more seconds and we'll go back to the questions. Okay, thank you guys for your answers. Let me share my screen. Okay, so the second question we got was for a simply supported non-continuous concrete deck bridge, how could we prevent the spans overlapping with each other due to the seismic movements at the joint locations when performing a seismic dynamic analysis, sorry.
Okay, I'm just going to read this quickly to myself so I understand it properly. Okay, so I'm assuming what you mean by that is if you have two separate superstructures, more or less, that could move independently one from another. So going off of that assumption, I hope I'm assuming that correctly. But I mean, the reality is if they're separated, I don't know that you're going to necessarily prevent them from overlapping. But thinking about it from a real world perspective, if they were to overlap, they wouldn't necessarily overlap, right? They just slam into one another during a seismic event. So if you want to try and avoid something like that, then you may want to consider providing some sort of way to have those move together. You could connect them with a rigid link or an elastic link of some sort. Maybe they're not perfectly rigidly connected, but I hope I'm understanding the question correctly. I apologize if I'm not, but generally speaking, I mean, the reality is they wouldn't overlap in real life, right? You're not going to have them crossing, or I mean, they're going to hit into each other. So, and I've dealt with that before, and sometimes you expect it. That's an expected damage, and you're just going to deal with it if it happens.
Okay, I want to just share this one feedback from one of the attendees that said your power reactions are unbelievable. I thought
It was
that was very
ridiculous.
nice.
I can't remember how that came up, but it was crazy. My mind was blown, and it was amazing to me how such a small change could just, and then everything looks like it's behaving the right way. Crazy.
Incredible. Okay, and then the third question we got was where would you use an elastic link versus a linear spring?
Oh yeah, great question. So usually with elastic links, you're talking about connecting two nodes together in some way or another. So I think an elastic link would be a good place you could use that is if you had a bridge that's modeled with the superstructure separated from the substructure elements by space. You've got a node for the top of your support. Let's say it's an abutment or a bent cap or something, and that node, there's a gap between that node and then your superstructure or your beam elements but you've got a boundary condition or a support that has some stiffness to it. You would connect those two nodes together with an elastic link, or or a linear spring. Really, you can use them interchangeably. I mean, it's not necessarily that you have to do it a certain way. I've even seen, I think even MIDAS, let me just show you this. This is something that's interesting that I remember going through this once.
Do you want me to give you the presenter mode?
Yeah, can we do that? I want to
Yep.
just show this because you can use them interchangeably. All right, let me see. Okay, which one are you seeing?
I see the civil screen.
Okay, so if you go into point spring support, for example, you can model things with stiffness, or you can check these boxes and make it fixed. And what's different between that and a support? I mean, essentially nothing. It's basically the same thing. So if you were to create an elastic link between, if you were to create an elastic link between two nodes, now you wouldn't be able to use a point spring to connect two nodes because it's a support condition. So you would assign it to a node and it's a support condition, whereas like an elastic link, you would be connecting two pieces together with this. You got start link number. That would be your controlling node. So something I mentioned in my little presentation before was thinking about, what would control if your bridge were to move a certain way and you had a link between two nodes, which of those would control the movement? Now, if you had something that was super rigid, there was one example of, I'm thinking of a project where we had a rigid diaphragm deck, and it was like a through arch that was steel, and they were connected together. I had to connect the rigid diaphragm with the steel, and I had to think through, okay, well, which of those is going to control the other? If the bridge moves, which is going to be the controlling node, because you have to assign a controlling node whenever you're connecting nodes together with rigid links, like master node here. You have to assign that, because you can't have a scenario where you have a node that wants to go one way and a node that wants to go the other way. If it's a rigid link, one of those two has to dictate where it goes, right? You can't have them move separately, because that's the whole point of the rigid link. So you have to determine which is going to control. I know I'm kind of getting off on a little bit on a tangent here, but I think it's a relevant topic. So, and in that case, I think what we ended up doing was realizing that rigid diaphragm deck was going to control the movement more of this than the steel arch itself would, just because due to its rigidity. It's like you weren't gonna bully that deck into doing anything it didn't want to do. The steel arch wasn't going to be able to force that deck to do something it didn't want to do, because it was stiffer. It was just not going to move. So just depends on your scenario, I'd say, once again.
Okay, awesome. Let me check if we have any more questions. A lot of people liked your Princess Bride reference.
Nice. I think a lot of people are watching it.
Yeah, absolutely. I think you kind of you covered everything that everybody was really wondering about. I don't know if anybody has any more questions, please submit them now. I'll give you guys like another minute or so. But yeah. If not, I guess, yeah, we're kind of at the end anyway. So if you guys have any other questions that you would like Zach to answer, if you have questions about the software itself or the capabilities on this topic, feel free to let us know. You can email either myself, it's Luciana Farias, Farias, at midasoft.com, or you can email us at grow@midasoft.com. If you have any specific questions for Zach, you can also let us know and I can forward them to him. But yeah, Zach, thanks so much for the session. I know everybody really seems to have enjoyed it, every single part of it, honestly, based on the feedback that we're getting.
That's not
And
being just be my boring slides at the beginning.
Yeah, no. They still enjoyed the rest of the slide. Yeah, so like I said, this concludes our session. Thank you again, Zach, for this really great session. For anybody who came in a little late, we will be uploading this session to our page by the end of the day today. So just be patient on that. And yeah, have a great day, everybody. Zach, again, thanks so much. And yeah, thank you, everybody.
Oh,
Have a
thanks, Joe.
wonderful day. Bye.